So section 4.5, we're going to graph functions using not only what we've learned in college algebra and stuff like that, but especially things that we've learned in calculus. One of the first things that you could look at is the domain of your function. Where is it actually defined? You don't want to try and find critical points and critical values, inflection points outside of the domain because they're just not going to exist. Another thing is the function symmetric? In other words, is it an even function? And if you remember, there's a nice test for an even function. It's if f of negative x equals f of x. So that didn't come out terribly clear. My apologies. Let's see if I can't fix that a little bit. So if f of negative x equals f of x, then it's an even function, meaning it's symmetric with respect to the x-axis. You can also look to see if it's an odd function. That's not as visually striking. F of negative x equals negative f of x. That does have some nice properties for when you're working with integrals, but we'll get to that later. When you have rational functions, that is, some polynomial function divided by some other polynomial function, then you can look at horizontal or oblique asymptotes. Now, if the numerator is bigger than the denominator, then you can divide and look at the quotient remainder. So the remainder term is going to eventually kind of go away, so you'd just be left with a quotient. That's going to be roughly your asymptote. It might be an oblique asymptote, it might be a parabola or more, but more often than not, the problems that you're going to face are going to have horizontal asymptotes. Those are going to be when you have a degree in the numerator that's less than the degree in the denominator or equal to the degree in the denominator. Then you're going to get these horizontal asymptotes. So nice cases there. Horizontal asymptotes are also determined by looking at the limit as x approaches infinity or negative infinity. If that has a limit, then that's where your graph's going. So that horizontal line. So a lot of times on an exam, I'll ask you to calculate and show calculations for your asymptotes. If you can do this, find the limit as x approaches plus or minus infinity, and get a finite number, then you've got a horizontal asymptote. Intercepts, set x equals 0, find the y-intercept, and vice versa for the x-intercept. Critical points, so this is where your calculus starts kicking in. Critical points, where the derivative is 0 or doesn't exist. Where the second derivative changes sign, you're going to have points of inflection, so that's going to talk about concave up and concave down. And then, test some points. Put some points in between there. Bring all these things together to try and get a complete picture of what's happening with a function. So with that, let's start taking a look at a friendly one to begin with, which is going to be a polynomial function. And that's going to be this one right here. So the nice thing about polynomials is that their domain is everything. So the domain is negative infinity to infinity. So there's no problems there. Happy about that. Then let's see what else to think about. Well, nothing's going to jump out in terms of horizontal or vertical asymptotes because it's not a rational function. So let's see if we can't find some critical points. Y equals x to the fourth minus 8x squared plus 8. I guess one thing that does jump out in my mind is that because these are all even exponents, this is going to be an even function. What does an even function tell me about the graph? Yeah, it's symmetric. It's going to be symmetric with respect to the y-axis, so that's a good thing to know. So the left-hand side and the right-hand side of this graph should be mirror images of each other. Let's look for some derivatives. Jameson, what would dy by dx equal?
4x to the third minus 16x.
Nice, nice. And then we also need the second derivative, d squared y over dx squared. Laura, what would that one be?
12x squared minus 16.
Perfect. 12x squared minus 16. Now it's going to be helpful for us to know where these are both equal to 0. So let's first of all set the first derivative equal to 0. 4x cubed minus 16x. From that, I think I'll factor out a 4x. And that'll leave behind x squared minus 4. And that's going to factor a little bit more as x minus 2 and x plus 2. So overall, where that's equal to 0 is going to be at 3 places. X equals 0, x equal 2, and x equal negative 2. All right, looking good there. Let's find where the second derivative is equal to 0. So where the second derivative equals 0, that's going to be 12x squared minus 16. I don't think we're going to get nice warm fuzzy points from this one, but let's see what happens. So 12x squared minus 16. I can factor out a 4 from both of those. 4 times 3x squared minus 4. And that's going to factor a little bit further. Let's think. 4 times, let's see, square root of 3x minus 2 and square root of 3x plus 2. So that's going to give me roots at negative 2 over the square root of 3, negative 2 over the square root of 3 and positive 2 over the square root of 3. You could get that by just setting this middle term equal to 0 here and using the square root property. You're going to get the same thing. But let's make ourselves a little bit of a table here to kind of keep track of all this information and figure out where it's increasing and decreasing, that kind of thing. So I'll start with the first derivative, x, f prime. We had roots at negative 2, 0, and 2. It's very helpful to put these in order in your tables. So let's do a little table for all of these. Now the derivative itself is 0 at these points. We already know that. That's what we calculated. We need to determine the sign of the derivative in between these points. So we can test some points for that. Let's see. One easy way is to plug those into your calculator. So plug in the first derivative here, 4x cubed minus 16x. And we're going to need to make sure we do some test points. Just kind of a quick little look here. Yep. Make sure you get your calculator's table set up correct. Independent should be set to ask. Dependent should be set to auto. You can find that window by hitting the second key and then the window key up top. When that's all set, we're going to test some points. Let me get rid of the ones that are already here. I need some points to the left of negative 2, between negative 2 and 0, between 0 and 2, and then to the right of 2. So what would such points be? I don't know. Negative 3, negative 1, 1, and 3. Those seem to work. So negative 3, negative 1, 1, and 3. Now, what information am I looking to get out of this? I mean, it's really interesting that the first derivative has a sign of negative, or is equal to negative 60 at negative 3, but, I'm being a little bit sarcastic there about saying that it's really interesting. What information do I really need from this table? What am I going to put down on this table? Yeah, if it's negative or positive. And this one went negative to positive, negative to positive. So, great. what's that telling me is happening with the function to the left of -2? It's decreasing. And then it's increasing. And then it's decreasing, and then it's increasing. And from here, you could fill out, where it's increasing and decreasing, etc. in general. We're going to graph this, so I'm not going to bother listing those kind of things here. But it does kind of tell me a little bit about what's happening at -2. The function's decreasing until it gets to -2, and then it starts increasing up to a point at 0, and then it starts decreasing, etc., down to +2, where it starts increasing again. So at the very least, these are local mins. In fact, I think they turn out to be global mins. Let's work with the second derivative. Plug in some points there. So make ourselves another little table here. So x, f, f double prime. This time we've only got 2 points to deal with. And those points are going to be 2 over the square root of 3 and -2 over the square root of 3. I'm not sure I really left myself enough room to draw those points here. Let's see what we can do this way maybe. -2 over square root of 3 and +2 over square root of 3. Now, I'm not sure about you, but I don't know the exact value of these things. So in terms of testing points, you might have to do a little bit of work up front. So 2 over the square root of 3 should be about 1.1 something, 1.2 maybe, kind of. Let's find out what the value of that is. So 2 divided by the square root of 3 is really 3 to the 0.5 power. Yeah, okay, so I was pretty close. 1.15. So in terms of testing points, we need points to the left of that, between this, and then to the right of that. Now, before I do my testing points, there's one thing I got to be sure of. What is it? What do I got to do before I start testing points in the second derivative? Antonio? Well, yeah, they're all in the domain. That's good. You should always think about the domain before you go looking for test points. But as far as plugging that into my calculator, there's one important thing I really got to do before I start testing values in my calculator. I got to put in the second derivative, right? I don't want to test points for the second derivative in the first derivative function. So I've got to change this now. It's going to be 12x squared minus 16. Now I can do my test points. As far as those are concerned, you can get rid of your old test points. To me, it's a good idea to do so you don't get confused. You can just type right over them. That'll work as well. But without thinking too much, I don't know, -2 is going to be to the left of that, so that should work. 0 is a nice one in between it, and 2 is to the right of it. So easy peasy. -2, 0, and 2. Positive, negative, positive. Okay. And if you thought about what we're looking at, a quadratic polynomial, maybe we could have come up with that without necessarily going through all the fuss of testing points. Positive, negative, positive. Rahana, what's that telling us about the function here? Concave up,
Concave
down,
concave
and up. Nice. So now you've got enough information to try and piece together this function. Now, typically speaking, you might need to find these points for yourself by plugging in these points, -2, 0, 2, -2 over root 3, and 2 over root 3, into the function to get these points. But I've done that for you so that all we have to do is play connect the dots in kind of a logical way. We know that the function is coming down and down and down forever until it gets to this point at -2, and then it starts going up. What special thing is going to happen? How come I have this point here? Anyone suggest a reason why I've got this point here on my graph at all? Yeah, it's an inflection point. That's where the concavity changes. So this one's an inflection point. This one's an inflection point. These are going to be absolute mins, and this one's going to be a relative max. So the function goes from increasing to decreasing. That point's going to be a max. So it's a matter of playing connect the dots. Now I do think I put a link out on Desmos there. So if you wanted to take a look at the graph, it's going to look kind of like this. Let me see if I can't make it look a little bit prettier. Something like that. And then of course, then you could throw in your concavity points, your inflection points right here where the function changes concavity. It'd be tough to find that without calculus. It's not at all obvious to me exactly where this function changes concavity. Where does it stop being concave up and start being concave down? So, okay. But like I said, the rest is playing connect the dots. One thing you should count on is that your graphing calculator is not going to get everything done for you on the exam. You're going to have to know your calculus in order to be successful on the exam. But you shouldn't throw your calculator away just because we've got all this calculus. We're going to be using the calculator a lot, not only in this section, but especially in section 4.6. All right. Comments or thoughts on this first one, example A? It's kind of a nice intro example to all of this stuff. So not a bad idea to go through this one as a warm-up. But let's keep going with some more here. I think this is the next one. Let's just double check on that. Yeah, there we go. All right, so example B. Now I did you a little bit of a favor in example B, and it's not unknown that I do this on the exam. What favor do you think you see for yourself on example B before we really even get started on this? Yeah, I gave you the first and second derivatives here, right? So, wow, pretty nice. That's because, you know, sometimes this involves a little bit of extra skill in factoring in order to get these kinds of things. So maybe I just want you to have the right values here, or the right functions, so that you can decide for yourself, do I really understand what's going on here? What are your thoughts? Where would you start? What's catching your eye first? Lucas, still dealing with the time change? A little bit? All right, yeah. I feel your pain. Anyone, where should we start? What gets your attention first?
Start with the first derivative.
First derivative? Set some derivatives equal to 0. Okay. Start with the first derivative. Before we even get there, let's think about the domain. There's something about the domain that is certainly worth your attention. Now, what is the domain? The domain is a set of x values you can put into a function, right? Can I just put in any old value into this function I want? No? What could go wrong? Oh, yeah, 5. If you put in 5, that's going to give you a problem, right? It's not going to be defined when x equals 5. What other value is it not going to be defined for?
-5?
Yeah, -5, right? 5 or -5, right? Both of those are going to create problems. Now, if you actually were to look at the function and play around with it a little bit, we'll see. I could factor out the x from the numerator, x times x plus 5. And the denominator factors as 5 plus x times 5 minus x. So you can kind of see in the denominator that when x equals -5 or x equals +5, the function's undefined because you'd be dividing by 0. But there's something interesting about x equal -5 that doesn't exactly come through if you just looked at the denominators. What's interesting about x equal -5? It looks like you can cancel out this term. Now keep in mind, this isn't defined when x equals -5, but boy, if you canceled out that term, it looks like everything would be pretty nice. We saw this back in chapter 2. What kind of a feature am I going to see at this point in the graph? A hole. There's going to be a hole in the graph. So everything is nice and defined up to the very point that you get at x equal -5. Then there's a hole. It's just undefined there. So now, in contrast, do you have a term like that canceling out the 5 minus x over here? No. So one of the big features you're going to get there is a vertical asymptote. So let's write down the domain. The domain is everything except -5 and 5. And then at x equal 5, you've got a vertical asymptote. At x equal -5, you've got a hole. X equals 5, vertical asymptote. And then x equal -5, there's a hole. Okay. All right, so let's put in our vertical asymptote. That's going to be at x equal 5. I'm going to draw that with a nice horizontal or dashed line. Make that a nice bright orange. I'm putting it as dash because I don't want you to confuse this with an actual part of the graph. It's a feature of the graph. You'll kind of see it, but it's not actually going to be part of the graph itself. What else can we see? Well, because this is a rational function, that's this kind of stuff. We can look at, well, what case is it, and see if we can't find a horizontal asymptote or maybe an oblique asymptote. So there's 3 cases. There's a case where the numerator degree is less than the denominator degree. There's the case where they're equal to each other, or there's a case when the numerator degree is 1 more than the denominator, in which case the quotient becomes your slant or oblique asymptote. Which case am I dealing with? A, B, or C? B. Yeah. So it's case B. Now, let me maybe rewrite our equation one more time. Let me do it over here as y equals x squared plus 5x over -x squared plus 25. So I just turned it around the denominator, but what I want to highlight is the fact that these two are the same degree, so it's the leading coefficients that are going to tell me what the horizontal asymptote is. It's the ratio of those two. So our horizontal asymptote is really going to be y equals, and it's going to be a ratio. What's the leading coefficient in the numerator? And in the denominator? -1. So y equals -1, that's going to be the equation of your horizontal asymptote. And you can actually see that with calculus. If you took a limit, or the look at the limit as this approaches infinity or negative infinity, that limit is going to go to -1. In fact, what's one way you can calculate that limit? It's kind of a nice dovetail on stuff that we didn't cover last Thursday, or no, last Wednesday. Does anyone know what you could do to find that limit? So, kind of a real quick look at this. The limit as x approaches infinity of x squared plus 5x over -x squared plus 25. maybe not too many people are watching the videos that I posted online yet.
Can we use L'Hopital's rule?
Oh, yes, we can use L'Hopital's rule. All right. So because if you try to plug in infinity, you would get infinity over infinity. That means you can use L'Hopital's rule. Well done, James. So that becomes a limit as x approaches infinity. What's the derivative in the numerator? 2x plus 5. And the derivative denominator is negative 2x. Oh, but then we try and plug that in again, and you're also going to get an infinity over negative infinity. So now what? You can actually, Maj? Maj?
The rule again.
Yeah, apply L'Hopital's rule again. So this is going to become the limit as x approaches infinity of 2 over negative 2, which of course is just negative 1. So that's, there again, there's your horizontal asymptote. So let's put that feature into our graph as well. So that's at y equals negative 1. Now your graph should kind of dance around both of those features. It can cross a horizontal or vertical asymptote. A lot of times it'll stay on one side versus the other, but it can cross that. Now, let's look at the first and second derivatives here. So our first derivative, call it y prime, is 5 over x minus 5 squared. Let's make ourselves our standard little chart, except, good question, where can the numerator equal 0? Where can this function equal 0? It actually can't equal 0. This could only equal 0 where the numerator equals 0. But 5 doesn't equal 0, so it can't equal 0. It can change signs, though, at x equal 5. From one side of the asymptote to the other side of the asymptote, it can change signs. So let's put a 5 in here and test some points. And let's see. I'm not going to bother taking out a calculator. If you plugged in something to the left of 5, like 3, 3 minus 5 is negative 2. Squared is going to be a positive. And a positive divided by a positive is positive. Same thing's going to happen on both sides. So Alex, what's that saying about our function? What's it doing to the left of 5? What's it doing to the right of 5? So, yeah, so it's basically it's always increasing. Now, if you're asked on WebAssign, where is it increasing? Please don't put infinity to negative infinity to infinity. It's increasing from negative infinity to 5 union 5 to infinity. So you're kind of dancing around that 5. Remember, 5 is not actually in the domain of this function. Actually, I should probably put around negative 5 as well. Yeah, because it's at negative 5, it's undefined. So I should really extend this a little bit and put around negative 5 to 5. There we go. All right, so now that covers everything because negative 5 is not in the domain. All right, let's look at the second derivative. Y double prime equals negative 10 over x minus 5 cubed. By the way, when I was calculating these derivatives, do you think I used the quotient rule for this one? No, I wouldn't. I mean, if I were you, if I was calculating that derivative, I would rewrite that as y equals 5 times x minus 5 to the negative second. What's the advantage of writing it this way? There's no quotient rule. What rule do you have to use? The chain rule. So it's -2 times that gives you your -10, and then x minus 5 to the -3rd times the derivative of the inside. But what's the derivative of the inside? It's 1. So you get to that pretty quickly. So y prime equals that. Nice. Let's do ourselves a little table for this one. X, F, F double prime. 5. You know, I'm wondering if I need to also test points on either side of -5. I don't think the function is going to change signs around -5. I think it can only change signs at x equal 5. So you know what? I don't think we have to look at this one. There we go. Never happened. Let's test points to the right of 5 and to the left of 5. To the right of 5, let's just do a little thought experiment. Pick a number like 6. If you put in 6, 6 minus 5 cubed, is the denominator going to be positive or negative? Positive. And a negative in the numerator divided by a positive in the denominator gives me what kind of a quotient? Negative. To the left of 5, say like 3. 3 minus 5 is negative. Cubed is still negative. So a negative divided by a negative is positive. Now that's telling me that the function is concave up and then concave down. So, all right, looking good there. And I can say goodbye to this one and this one. Overall, let's put in some information here. Let's take kind of a look at the graph. I'm not taking your graphing calculators away, so you can just graph these things and make sure that your graph matches, you know, what the graph has in the graphing calculator. Now, keep in mind that the graphing calculator is not going to be able to show you the hole in the graph. I mean, even decimals doesn't show you that unless you're really, really careful and clever. So you can see the concave up shape to the left of your vertical asymptote, concave down shape to the right of it. You can see the limit as x approaches infinity and negative infinity. Either direction is -1. If you wanted to be really cool and careful and clever, you could make sure that your graph passes through 0, 0, which is the x and y intercept in this graph. That's great if you do. I'm not terribly worried about it in this particular case if you don't, but like I said, it's great if you do. All right, so something like this. So I've got the big features of this graph, except right here, I need to put a little hole. You can actually find the coordinates of that hole. You can find the coordinates by calculating the limit as x approaches -5 of that. You can get that limit in one of a couple ways. You can use it with L'Hopital's rule, or you can just cancel out those and take a look at the limit. I think you'll get -5 and 1/2 would be that hole. -5 and 1/2 for the hole. Nice. Okay, a lot going on with that one. If you need me to back up a little bit and mention something again, that's great. If not, we can move on, but whatever works for you. So, a lot going on with those. I am going to give you a chance today to do some practice on your own. Trying to hit some of the highlights here, some of the things you should keep in mind as you go through these graphs. Let me keep rolling. All right, so our function here, and let's see, I guess we'll call this what? Example C. Let's just double check my decimals here. Yep, example C, let's shut those off. Here's a look at the graph. Example C. So y equals x to the 5/3 minus 5x to the 2/3. Now, you could rewrite these with roots. It's not going to help you differentiate things, quite the reverse. Cube root of x to the 5th minus 5 times the cube root of x squared. Can you take the cube root of a negative number? Cube root of negative 8? What's your calculator say if you try to take the cube root of negative 8? What do you get? You get negative 2, right? So you can take an odd root of a negative number. And the reason I want to point that out is because these are defined for all values of x. The place to start with your work here is the domain. The domain is just going to be negative infinity to infinity. There's no restrictions on this function like there was in the last one. Nice. Where should I go from there? What should I work on next? Yeah, some derivatives. Great. So let's work on some derivatives. Now, as far as the derivatives are concerned, dy by dx, I'm going to use this form rather than this form. Makes a whole lot more sense. So it's going to be 5/3 x to the negative, no, actually x to the 2/3 minus 10/3 x to the negative 1/3. Now this is a great place to have this in terms of finding the second derivative. So maybe we'll find the second derivative before we start playing around with these things. So what would the second derivative be? Try and calculate that. And then we'll start trying to clean these things up a little bit so that we can't figure out inflection points, increasing, decreasing, minimums, maximums, critical points, all that good stuff. Aram, what would be the second derivative here, please? What do you get when you differentiate?
2/3, so it'd be 10/6.
10/9, right? 'Cause 3 times 3, yeah. 10/9, x to what power? Well, if we subtract 2/3 minus 1 would be negative 1/3. And then let's keep going. Ram, what about the next term? What are we going to get here?
Plus
Mm-hmm.
plus 10/9
Mm-hmm.
x.
Negative 4/3, right? Because you're going to take 1 minus 1/3. If you're struggling with these things sometimes, it's okay. There's no shame in that. Don't feel embarrassed, especially if you're worried about other things on a test. You can just take things like negative 1 divided by 3 on your calculator and subtract 1. Now, it's probably going to give you a decimal value, and if you don't recognize that decimal value, no big deal. Hit the math key. Boom. At least you got it right, all right? I'm not worried about your arithmetic skills. I've got bigger fish to fry. I want you to make sure you can do the calculus part. Now, we're going to need to set each of these things equal to 0 and find critical points, that kind of thing. Let me take care of this negative exponent and start working around with the other part of this expression. I'm going to write that as 5x to the 2/3 over 3 minus 10 over 3. Yeah, it should be a better looking 3 there. 3x to the 1/3. Great. Except these don't have common denominators, do they? No, they don't. It'd be nice if they did have common denominators. So what do I need in order for this to have a common denominator with this? What am I missing there? X to the 1/3. So let's introduce that x to the 1/3. Now the only way you can really do that is to multiply by 1. So x to the 1/3 over x to the 1/3. Now yeah, it does cancel itself out, but if we avoid canceling that out, then what are we going to get? Then we're going to get 5x to the first power minus 10 over 3x to the 1/3, and that's our first derivative. Let's try that again over here. I'm going to give you a chance to work on some of that. Both of these terms have negative exponents, so I'm going to bring them down to the denominator. That's going to be 10 over 9x to the 1/3 minus, or plus 10 over 9x to the 4/3. Again, I need a common denominator. Alex?
Did you not have combined them before putting things down in the denominator?
No, because these are different exponents. They're not like terms. So it's like adding x cubed and x to the 5th. You have to have the same exponents. Appreciate the question though. Thank you. What would be the common denominator? We've got a 9 in both of them, so we're okay there. The common denominator is going to be that'd be the greatest common factor would be x to the 1/3. The common denominator is going to be the larger of the exponents. So it's going to be the 4/3 there.
You just multiply by x.
Yeah, and just multiply by x. Yeah, so we need one more x, right? If you take 4/3 minus 1/3, the difference is x to the first power. So multiply by x over x, and that's going to give me 10x plus 10 over 9x to the 4/3. So one way or another, you're going to need to arrive at this conclusion for your first and second derivatives. Great, so we spent a lot of effort getting our first derivative. What are we going to do with that first derivative? We need to find the critical points. So how do you find the critical points? Set what equals 0? All right, so where the numerator equals 0 is where the derivative is going to equal 0. That's going to be a critical point. Where the denominator equals 0 is where the function is undefined, where the derivative is undefined. So that's also going to be a critical point. So the numerator equals 0. That's going to be 5x minus 10 equals 0, or x equals 2. The denominator equals 0. That's going to be 3x to the 1/3 equals 0, or x to the 1/3 equals 0, or x equals 0. So you get two critical points for the denominator. Bless you. Now I already know that 0 is a critical point, but it's also a point where the denominator can equal 0 over here. Where does the numerator equal 0? Nice. So 1 and negative 1. The denominator equals 0. That's going to be the same place that the denominator was equal 0 just a moment ago at x equals 0. All right. So let's make ourselves some tables here and try and line up this information with the graph. this one. So I've got x. I'm in the habit of calling it f and f prime. I'm going to stick with that. F and f prime. I've got points at 0 and 2. And x, f, and f double prime. -1 and 0. I'm going to need to be testing points on either side of those. Before I start wailing away on our table and testing points, what else do I need to do? When I take out my graphing calculator and start testing points, what else should I take care of? Yeah, I got to change the function. So I got to put in the first and second derivatives into my calculator. Now, I'm not sure if you want to get fancy and put them both in at the same time. You can do that. Nothing wrong with that. Let's be careful about something here. The derivative is 0 when x equals 2. But when x equals 0, the derivative is undefined. What kind of features on a graph would you see if a derivative is undefined? Remember, this was on the last test. Go ahead. An asymptote, right? Or more generally, where the function is discontinuous. I don't think we're going to have a discontinuous function here because the domain was negative infinity to infinity. But that is one of the points you can have, is a place where the function is not continuous. What other features of a graph would lead to a derivative not existing at a point? I know this is going back a little ways, you know. All right, got a vertical tangent. What else? Corner point, right? Corner point. So remember, the derivative is the slope of the tangent line, and it's a function of a limit. So a corner point is going to have tangent lines that are approaching different limits, so it's not going to exist. There's one other place that you could find a derivative that wouldn't exist, and that is if you had a vertical tangent. So we'll kind of see what we associate with this feature, but the first derivative nor the second derivative is going to exist at those points. So that's what I mean by this little symbol here. This means there exist. So this means there does not exist. Not exist. So that's what I'm using it for here. I need to know the sign of the function, sign of its derivatives in between these points. So let's plug those functions into our calculator. Now, you don't have to plug it in this nice, neat way here. You can plug it in like this. Whatever one's fine. To me, it actually looks easier to plug in this than it is to plug in this up here. So I'm going to plug in that one and this one. All right. Tell you what, I'm going to get a little bit efficient here. I only want to go to my calculator once. So we're going to plug in both functions. I'm going to hit the y equals key and clear this out. Now I'm going to put in this form of my function. So I'm going to put it in as a fraction. So I'll do it two different ways. Put it in using a little fancy trick here. If you hit the alpha key, then the y equals key, alpha and then y equals right there. The first option is for you to put in a fraction. So I'll just put in 5x minus 10 divided by 3, then x raised to the 1/3 power. If you have an older TI-83, for instance, you're going to have to put that 1/3 in parentheses. I'm also going to enter in my second derivative. I'm not going to use that fancy alpha y equals key with that one. I'm going to do it a little bit more generally that anyone can do. I want to put in this expression. If you're going to put in that expression, the only thing you have to do is be careful that the numerator is in parentheses. So 10x plus 10. I want that all in parentheses divided by parentheses 9x raised to the 4 divided by 3. and then to the right to get out of the exponent, and then one more right parenthesis. Now as I start testing points, I don't want to see y2 right away. I want to test points for y1. So here's the trick. If you cursor over to the left and press the enter key, now let's kind of step away from that a little bit. Notice that the equal sign is no longer highlighted. It's not going to show me the graph of y2, nor is it going to show me the table results for y2. It's just going to give me y1. So that's good enough for me right now. Let's go to the table and test some points. Let's delete all the ones that are here. Keegan, what would be some good test points in and around these here?
-1, 1, and 3.
Sure, -1, 1, and 3. Perfect. Let's test those points. Thank you, sir. -1, 1, and 3. Nice. Iris, what information am I looking to get from this table? Yeah, direction the graph is growing, and that's told to us by what?
The sign.
Yeah, and the sign goes positive, negative, positive, so it's increasing, decreasing, and increasing. Nice. Before we turn our attention to the graph, let's finish up our testing of points. Thank you, Iris. Olivia, I need some more test points. So something to the left of this. Go ahead.
-2, -0.5, and
Perfect. -2, -0.5, and 1. I like that you gave me a nice decimal value. Sometimes you're going to have to use decimal value. We'll see more of that in section 4.6. All right, so those are good test points. Before I test those points, go to the y equals key, the equation editor. Let's shut off this equation and turn on this one. So that way I'm going to get results for the second derivative, not the first derivative. Nice. Hit the second key, then the table key. Let's delete these values here and plug in Olivia's values, -2, -0.5, and 1. Interesting. Now, a lot of times what you'll see in these things is that the signs will alternate, positive, negative, positive, that kind of thing, but these didn't. That's okay. So let's see. We got negative, positive, positive. I'm trying to think about the graph and justify that. I think I can. I think it makes sense in my mind, but we'll see when we actually look at the graph. So negative, 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 positive, positive. So it's going to be concave down, concave up, and concave up again. Now, there's nothing wrong with looking at the graph, although I like looking at it after I get this information to make sure that what I'm seeing from the graph matches what I'm seeing here. For instance, I should see it increasing, then decreasing, then increasing, concave down, concave up again. Let's check it out with the graph. And let's throw in the critical points here. You know, I probably should have done something like this. I put them in a table. Bam, bam, bam. Wait a minute. Something's not looking right. Oh, okay. Yeah, there we go. 0 and 2. So why are we getting a critical point at x equals 0? Yeah, you got a corner point there, right? You get that sharp edge. That's why you're getting that critical point. But to the left of this, And it's boy, it's just impossible to see here. But check it out. To the left of this graph, what's its shape? To the left of -1, I should say. Concave down. I mean, even with a little statistical torturing and my skill at working with these graphs, I can't make that thing look like concave down very much. It almost looks like a straight line. And yet, it is concave down, and over here it's concave up, and then here it's concave up as well. So, nice. Let's sketch in that graph, play connect the dots, and I think we're done with that one. Whew. Yeah. Can't really get that one to look concave up, concave down. So nice. Nice. And then you can fill in the intervals, if you're asked to, where is it concave up, where is it concave down, that kind of thing. You could fill in all that information. So there's a critical point there. There's a local min. This is an inflection point. That's just your x-intercept. Nothing special is happening there other than it crosses the x-axis. But it was concave up right here, concave down, and then concave up. So those are all of the features of the graph. Please do pay attention. Sometimes on a test I'll ask you to label the features on the graph, and I do want to see them there. So I give points for that. Yes?
I don't understand how to set the first concave up 5 and
This one?
that one.
Oh. It doesn't look concave up, does it at all? It just doesn't. What we're relying on is this table. And this table said between -1 and 0, it's concave up. Yeah. I mean, you could look at this graph on Desmos and you could stretch it this way, that way, the other way a long time, and you just really can't see it. What are we relying on? We're relying on the calculus. The calculus says that the second derivative is positive here, so it has to be concave up. No, I totally agree with you. I mean, we're really at the mercy of the math there. That's what it's telling us, so that's what we label it. But did I draw a concave up? No, I just drew a straight line because I knew I couldn't come close to that. So, yeah, thanks for asking. Anything else on this one? Okay, I think we got one last one in this series. Actually, we got let's see. There's a couple mystery functions. This one here, and I'll let you kind of guide me through it. It's a little bit of a hint or a taste at what's going to come up in the next section. No, you know what? We should have one more. Should we have one more? No, let's see. Example D. Am I missing example D someplace? No, we're just going to go with the mystery function next. So let me shut off these and move down to the mystery function. Let's take a look at a couple things that we know. I've given you some points here, and the question is, how are you going to connect these points? So one of the things you're going to need to play around with is the first derivative and the second derivative. So make ourselves a little table there, and I'll let you help direct me as to how to fill some of these things in. But we've got a few things. Let's look at this part right here. The limit as x approaches negative infinity of f of x is 0. What's that telling me? What do I get out of this? Ethan?
When you go left, starting at -4, it can't cross the x-axis.
Well, it could, but it's eventually going to settle down. So it could kind of wiggle around a little bit. But eventually this graph is going to settle down near what? Near 0. So eventually this is going to have a horizontal asymptote. Horizontal asymptote of y equals 0. That's what that's telling you. Am I going to get a horizontal asymptote of y equals 0 in the other direction? No. No, it's going towards negative infinity in the other direction. So it kind of seems like this thing just plummets right here. Now that's all we've got that's kind of given to us, but we do have the option to maybe look at some points. What does it kind of look like might be happening at x equals 0? Could be a corner point. All right, and if it's a corner point, then what kind of, what do you think you'd see with the derivative at a corner point? What should happen? Should be, actually if it's a corner point, it'd be undefined. So, let's see. You know, I didn't set this one up the way I thought I did. Rats. So, what we could do is we could test the function and its derivative at these points. I think the derivative at that one is going to be 0. So we can do a little testing of points. And let's see, do I want to test a couple points? I don't think I need to test that one, this one maybe, and then this one. I think these are going to be points for concavity, so let's just test 0. So you want to test to the left of 0 and to the right of 0. And to the left of 0, the derivative is positive. To the right of 0, the derivative is negative. So, okay. What's that telling me about my function? Increasing and then decreasing. So 0 has to be an absolute maximum. It can't deviate from that. I mean, you can't get any bigger than what's going to happen here. If the function is increasing until it gets to this point and then decreasing afterwards, that has to be an absolute maximum. How about the second derivative? I think there's a couple points that are going to be of interest in the second derivative. And let's see. All right. So second derivative is h double prime. What we can do is we can look at h double prime in a couple places. H double prime. Let's see. I'm guessing that there's an inflection point here and maybe here. Let's test a couple points. Let's test at -3. No, is it -4? Yeah, -4, -1, and 0. Let's test h double prime at those points. So h double prime of -4. Oh, it's positive. Okay. How about at -1? Then it's negative. And about at 0. Undefined. Undefined there. Yes?
I think the h function is not the right function.
Yeah, I'm wondering if, oh, you know,
Because it's already set.
let's take a look here. Yeah, the h function is the wrong one there. 'Cause that one doesn't, let's see. Let's call this one, say, n of x. And then let's do n of x. N of -4. It's negative. -1. Ah, boy. This isn't working out like I expected. There's something wrong with this. My apologies. There's the first derivative. Boy, that one. You know what? This is just not matching up very well, is it? All right. Let's assume that I have some kind of a mismatch here. So if we test, and I'm just going to have to guess at these values, but I think I'm right in this. At x equal -1, and yeah, just x equal -1.
I found a function, it's b of x.
Is it b of x?
B prime and b
Okay.
prime.
You sure it's b of x? I thought b of x was the next one. All right.
It looks like it.
All right. Let me just put in b of x. Actually, you know what? B of x. Yeah, I have that down here. So b of
Points in the table match that one.
-1. Oh, points match that one. All right, there we go. Let's zoom into there. So b prime of -1 is 0. All right, that makes sense. That means that to the left of this, say -2, the first derivative, the second derivative is positive. That's kind of what I was expecting. So if the second derivative is positive, then it's going to have a concave up shape. Let's see what happens to the right of -1. So to the right of -1, let's say -0.5. The second derivative is negative, so that it's concave down. And I don't think it changes after that. We can try a couple more points, like 0 and 1 and 2, 3, etc. So it keeps on remaining negative. So we've got this behavior, concave up and then concave down. So what's that telling me about this point right here? There's an inflection point. So this is an inflection point. So it's going to change behavior of the function. Overall, this function is going to behave as increasing until we get to here, then decreasing from there. Your concavity changes right here at this point. So concave down, starting it here at -1. So something like this. So we've got an inflection point, and then an absolute max. You've got an x-intercept. And probably one more feature that I'd appreciate seeing in this graph would be this one. That y equals 0 is your horizontal asymptote. Nice. At least out to the left. Whew. All right. Kind of a long one there. Comments or thoughts on this last one? Yeah, please.
So like for the ones where we're given like the function, like use the numerator and the denominator to get the x points. But I kind of lost you. How did you get the x points for the mystery function again?
So for this mystery function, I was kind of playing around with these points that are already on the graph based on this stuff right here, and I knew interesting things might happen and should happen here. So I took a guess that 0 might be some kind of a maximum point. So I tested points to the left of that and to the right of that in the first derivative. You can also look at the first derivative there and find, and those points are right here. We could do, for instance, b of 0 or b prime of 0, and that's 0. So that's telling you that x equals 0 is a critical point, and that if you test points on either side of that, say to the left, the function's increasing, to the right it's decreasing. So that matches what we kind of see from the graph. But yeah, this didn't work out quite as fluently as I liked, because I got a little mixed up with where I should be highlighting some of these things. I think we should have been using this one, Mr. Example, or this mystery function as opposed to the one that I was using. So my apologies for the miscommunication on that one. And as far as this is concerned, and I took a guess that, something would be happening here at this point for me to include it. So if you test this in the second derivative, you get a 0. And then to the left of it and to the right of it, the second derivative has different signs, so that's an inflection point. All right.
So you just kind of test the points that are already given.
Yeah, I played around with the ones that were already given and tested around there. Yeah. All right. Anything else? Let's put this one away.